So, okay everyone, so I'll caveat this talk by saying I did get a C in GCSE Maths. I did study art. There might be a couple of things in here that a mathematician might take offence with, but I have written a lot of applications that use matrices and they work. So it should be good. Okay, I'm going to start off with transformation matrices, what they are and what their minor applications are. So put simply, a transformation matrix is a way of storing the position, scale and rotation of an object in a multi-dimensional array. So it's done in rows and columns, presented as a table. Now a matrix doesn't have to be a 4x4 matrix, it can be any derivative of that, so you can have a 1x4, you can have an 8x8, you can have anything, so there's just lots of different ways. But a transformation matrix, certainly the way that Maya uses it, is always a 4x4 matrix. I'm going to draw one up on the screen and we're going to break it down. Just checking my notes, make sure everything. So yeah, the matrices are really the backbone of any 3D graphics software. It's really what makes everything work in an application like Maya, or in a game, or certainly in animation. You'll see later on how skeletons and hierarchies work and how dependent they are on matrix maths to make them actually operate. So let's start off with our simple matrix. Great big brackets, and we're going to have 1, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 0, 0. And this is going to be 0, 0, 0, 1. Okay. That's bracketed off, and then you'll see it presented like this in Maya as well. So what you've got there is one big list of 4 small lists. I'm going to break that down into what those are. I'll apologise in advance if this is all teaching people stuff that they already know, but I thought if I started at the beginning then it would make more sense. So this first area that I want to talk about is this. Now this is a 3x3 rotation matrix. And that is presented as the first column, the first row is X, this one is Y, and this one is Z. And you see that's pretty unfamiliar if you're used to Euler angles, which is what most people work with. The reason that is that this is actually presented, what this actually represents are 3 vectors. So a vector obviously is something that gives you length and direction. And in an identity matrix, that's something that's just sat at origin at 0, 0, 0. And what that looks like is a little something like this. So you have Y, X, and Z axes. So if we take this first row, that's the X row, have I done that the right way? Yeah, I think I have. Yeah, X, Y, Z, yeah, I have, yeah. So in the first row, along the along the X axis, we are at 1, where everything is always 0. This is why it doesn't go 0 to 1, because when you're talking about vectors, you always assume that the first coordinate is 0. I'm sure we all know about plotting points on a graph, where you go from point X to point Y by giving the coordinates of X, Y. This is the same thing, but it's in 3D. So we've got 0 here. And then it's 0 units up in Y. There's Y here. And it's 0 units along in Z. Now the Y-axis is going to be 1 in Y. It's going to be 0 in the other axis. And the Z-axis is going to be 1 in Z. And what that gives you is effectively this. So that's at 0, and it's something that is just formed just like that, just go straight across. So how do we rotate this? So if I wanted to rotate this matrix 45 degrees in the along the Z-axis, what you would end up with, I'm trying to think what pen to use for this, is something that looks something like this. And that would bring you to this point here. So we're just going to assume that that's a 2D plane, because if we start doing 3D stuff on here, I won't be able to draw it well enough. So at this point, you are 1 in the Y-axis, and 1 in the x-axis, but you are 0 in the z-axis because you haven't got any translation in this direction. And what that gives you is a rotation of 45 degrees from that position. And that's effectively how all rotation is dealt with in Maya. So if you had something that went straight off in this direction, this is quite hard to represent in 3D. Because effectively you're having something there and it's sort of coming out that way. Then you would start talking about how you're using a little bit of Z, a little bit of Y, a little bit of X, and you end up with this coordinate here. And you build that into your matrix. Does this all make sense so far?
Yeah.
The rotation. So the thing to remember is that as far as a computer is concerned, rotation doesn't exist. It doesn't store it, it doesn't compute anything as Euler angles. That's something that's just made it easier to present to the user. Everything's actually being done in terms of points in space. So these are actually all just three-dimensional coordinates for the x, y, and z axes. So always just remember that solid thing. You can't squeeze those axes, you can't move them, they are just oriented all around. Okay? Which brings me to my next bit. This section of the matrix here, this is very simple. This is the simplest thing. This is just the position. It's just the position past triangles, and it's just x, y, z. So very, very simple. If you've ever moved an object in Maya, you'll be very familiar with that. Which leaves us this last column, which is a bit of a strange one. Because what this is scale. And scale, because it has to be a 4x4 matrix and it has to stay this consistent shape, you also have to have a scale value in there for rotation as well, which isn't really that relevant to us. My green pen has died. So this is scale right here. And you see that on the position row, the scale is set to 1. Okay, and you'll see why this is relevant in a minute. Because this is, you'll be able to scale this later on if you want to change the position. The zeros here, they don't really matter. They actually could be 1s, they could be 0s. The only other thing to mention about how transformation matrices are normally set up is that you'll find that they're always, nearly always normalized. So if you were looking at these coordinates, it actually wouldn't matter if like that was a 5, and that was a 6, and that was an 8. It wouldn't matter because the length of these vectors is irrelevant. It's only the direction that matters. Okay, so that doesn't matter at all. Does everyone here know how to normalize a list of values or something like that? I won't go over that. It's a pretty simple equation. Go through that. So,
actually, do you think you could remind me?
Yes, absolutely. Yeah. Sorry.
I've muddled my way through.
Let me just do a very quick equation for doing that.
Sorry, everyone else.
No, it's a useful thing to know. So if we have a list, and the list is 1, 2, 3, 4, 5. What you need to get is the scalar, which is how much you need to divide each one of these values to bring it down to 1. So what we're going to get is our scalar, in this case, is going to be 1 over 5. But actually what you want, as algebraically, that's just going to be 5 over the max value in your list. Okay, so it's 1 over the max value in your list. And what that actually gives you is going to be 0.2. And then what you do is you make a new list in which you multiply every single one of these values by the scalar. So you say, I want x over scalar for x in list. Okay, and what that will give you is each one of these values will be scaled down, which will actually end up giving you, let's call that normalized list, and that's going to give you 0.2, 0.4, 0.6, 0.8, and 1. And that is where the highest value becomes 1 and everything else gets scaled down to meet that. And that's a way to quickly normalize a list. That's the way that you represent that in Python as a list comprehension. Okay, so that's that business over with. Normalising lists, something that we need to do a lot. But yeah, whenever you work with matrices in Maya, it will normally pre-normalise all the values. It only normalises the rotation values. If it normalised the position values, everything would end up smaller than one.
Yeah, that'd be weird.
Exactly, that's it. So I've given an example of how to rotate an object with those values. It is worth saying that when you're using Maya, if you freeze the transforms of an object, the rotation will be lost forever. Once it's frozen, as far as it's concerned, even if that's a cube on its side, that's it, gone. Okay, so you won't be able to retrieve that matrix, or otherwise it's just, the transform just gets reset to 0. Okay, and the next step, I wanted to talk a little bit about getting and setting matrices using CMDS or PyMel. So I think the way I'm going to do this is I'm going to switch onto the computer at this point now. So Oscar, if you're happy to begin the second camera,
Yeah.
I'll go over to this.
Face.
That's good, that's good.
Alright.
That's alright.
We're actually
Yeah, the lights will be fine. Don't worry, don't worry. Please take a seat over here.
Yeah,
Just no problem. No problem at all.
we're gonna cut out that.
Don't worry, yeah, I'll edit this later. I'll do the big crash scene. Are you pointing?
We're live.
Yeah, good.
Yeah.
Okay, I'm sure you can still hear me behind the telephone. That should be fine. So, getting and setting matrices. I'll go through a couple of little options. The simplest of which is going to be using Maya CMDS. It's mostly the same as getting any other attribute. Now, there's two ways you can do this with Maya CMDS. You can either say get attribute, and the attribute is .matrix. The way that I like to do it, and the way that I would recommend everyone does it, if you've not done this before, is going to be what am I doing? CMDS.xform. Xform is a very reliable way of getting any of these details. It's also very, very quick, which I like. PQ'd, that's the one everyone loves. And we go to query the world space. So we use the WS flag for world space. And we're going to say matrix equals true. And what that will give us is these values up here. And it actually comes back as a flat list. So what you'll see is that's the X chunk of the matrix, that's the Y chunk of the matrix, that's the Z, and that's the position with scale tacked on at the end. Okay, so that's how that comes back to you. Now, depending on what you use, if you use PyMel, that will come back as a PyMel data class, which actually presents that as a multi-dimensional array for the list of 4 lists. I'll show you just a quick example of how you can do that as well. If I can remember how to type properly. What am I doing, everyone? Is it? It's these wireless keyboards, they're rubbish. So just going to declare a Pinode. I'm sure you've seen this before.
I have not seen this before. But
Okay, so I'll take you through this. Oscar. That's absolutely
Some other
fine.
time.
Oh, that's okay. It will be done as part of this. So, so you make something into a Pinode by just passing it the string name, and what that gives you is this node here, and it's declared that as the node type is a transform object. But what this allows us to do is query particular attributes by just saying cube.matrix.get, and that gives you the matrix, and it comes back as this default matrix class. You'll see that it's just a list of lists over like that. The other thing that you've got in PyMel is there's a data type called Transformation Matrix, which you can cast this to, which actually has a few more extra built-in methods. It allows you do some really nice things, like you can set the transform, you can set the rotation, you can convert things to Euler angles, you can convert them to quaternions, you can do all of that out of the box from the transformation matrix. So that's the advantage of using PyML to deal with this sort of thing. The big disadvantage of using PyML is when you have to do any heavy amount of multiplications or any other kind of matrix math, it becomes incredibly slow. I wrote my own matrix multiplying method, and it was 16 times faster than PyML, and that was literally just zipping two lists together. It's very, very slow. But if you're doing something quick and you just want a very simple way to present this, and it's the way that I'll be doing the other examples, PyML is really not a bad place to start. Once you understand what you're doing with PyML, I would recommend that you immediately switch over to doing everything in CMDS. I've done comparisons between CMDS, XForm. I've compared that with Maya API, OpenMaya, and they are both, they're pretty much exactly the same speed. In some cases, it was even faster. So that's a very heavily optimized. XForm is a very heavily optimized thing, and you should just use it for everything. This is the best way of doing this. One thing I forgot to cover actually early on is why use matrices at all when you could just use the attributes. The main the transform and the translate and the rotation attributes. The main reason for that is that those aren't reliable indicators of where an object actually is. They normally give you the local space attributes, which aren't relevant if you're trying to pinpoint where something is in the real world. You could XForm the world space matrix and that would be fine, but if you're trying to, as later on when you start to put things into the space of other things, Euler angles become completely unreliable because they don't really work like that, and you get things like gimbal lock and other problems like that. The other way to handle matrices going through here, if you're doing a very, very heavy amount of matrix math, I would recommend using the NumPy library. That has a lot of built-in methods for dealing with matrices. It's incredibly quick. It has components of Fortran 74 compiled as part of it, so it's really, really old school computing maths, and it's really great for this sort of thing. Later on when we talk about the Frontier matrix library, that's all been done in NumPy, because it's very heavily optimized.
Is XForm, so I've used XForm to get the world space position of something before. Is that fairly reliable?
Yes. Yes, that is reliable.
It wasn't
Just
as
trying
a
to get the
matrix
position.
though, but yeah.
No, if you just get the position, because what that's actually doing is getting the matrix and subtracting the position from it and returning that to you.
Right. Okay.
So yeah, absolutely use XForm for stuff like that.
Yeah.
Use XForm if you want to get sort of just Euler angles and stuff from something, but when you start to manipulate those values, you'll soon want to start using matrices instead. So I'm going to go over some really simple applications of this. I've got my little test world set up here. You'll see I've got my three lovely cubes here, and I've actually got a bit of preset stuff here. I am using PyML for this just because it's going to keep what's on screen very, very simple. Declare my three cubes as a start. Alright, moving around. Right. Okay, so let's give a little talk about what we're going to do. So the very first thing that I do here is actually declare an identity matrix. An identity matrix is just a default matrix that is at origin. It has no rotation, and it has no transform, and it has just one scale value, just a uniform scale value. And that's the matrix that I drew up on the board earlier. As you see here, it's just presented in the same way. 1 all the zeros, 0, 1 all the zeros, blah, 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 all the way to the end where it's position 0, 0, 0. I just put that in there so that you can see what an identity matrix is like. That can be very useful if you're trying to move something relative to the origin. You can always use multiplications around the identity matrix. So the very first thing I wanted to show you, I'll put this in the wrong order, is actually just simply aligning two objects without using any constraints. The reason I wanted to show this is that in a lot of scripts that I see from people, they align two objects by creating a parent constraint with no offset maintenance, and then they delete that constraint afterwards. It's really slow, it's really hacky, and it sucks. What's a better way to do it is to get the matrix of the first cube, So that's your source object, and you're going to export cube 2 to that initial objects matrix, and what that gives you is that. Now something odd's happened there. You've probably noticed that the scale has also come across. So that's one thing to bear in mind when you are using matrices. If all you're interested in is aligning the position and rotating, you'll want to strip the scale value out of your matrix. And the way that you do that is to take that scale column in your matrix and just change it to 1. If you're dealing with a list of lists, very, very practical list of lists, then you just assign that the same way as you would in any other list. If you're using a transform matrix from PyMel, there's a set scale method that you can use. So you just say set scale 1, 1, 1, and that will just ignore the scale completely. The other way to do it is to break apart the matrix into its component rows and reassemble it at the end. And that's something that we do quite a lot in the F matrix library when you're manipulating them, so you can pick and choose what you actually want. So that's my first very simple example. You can do that over time. It's a really nice way of just, if you wanted to align a locator with a controller over the timeline, you just do that on every single frame, set the keyframe, and you'd have something very aligned, and it will be very, very quick indeed, particularly if you turn off the viewport while you do it. Another example that I wanted to give you here is finding the average position and rotation between two objects. And this gives a very simple example of how you can use matrices for basic operations. So the way to find the average between two objects, as I'm sure you all know, is you take the position of both of them and you multiply by that by 2, or however many objects you have in that list. You divide it by the same long way around. So I'm going to get the matrix of the first cube, I get the matrix of the second cube, and my average point is going to be cube matrix 1 plus cube matrix 2 divided by 0.5. Now the reason that I don't do divided by 2 is because matrices always contain a 0 at some point, and if you do a division by 0 it will crash. So instead we multiply by 0.5. But the nice thing about these matrix methods is that you don't have to do that for objects in the list. Simply adding two matrices together and then dividing the output of that just gives you the matrix. You don't have to do that in every element of the list. So that ends up with our average point, which gives us, please don't break. Right, there we go. So I'm going to export that. There we go. So we see that our green object has gone between those two objects and it's created, but you'll notice that something else has happened. It's gone all squished and weird. And the reason for that is because we just did a division on a load of 0 scalars. And you'll see that when we look in the channel editor, the scale is actually a bit all over the place because you've just manipulated that. So what I would recommend you do is, before you do any operations like this, strip any scale out of the matrix. Just don't acknowledge it or use it, because otherwise you get odd results like that.
How do you remove the scale?
So if you're using a transform matrix data type, like these are, you can simply call dot. Actually, I'll do it to this one that's been, I'll do that off the top of my head. Well, actually, I'll do it here. So you take your average point matrix and you go dot set scale. These keyboards.
Type slowly.
Yeah. Okay, sorry, it wants that as takes 3 arguments, 4 given. Is he going to be happy with that? Oh, yeah, sorry, I remember. You need to specify something else with the scale. Let me just bring up the browser quickly.
That's all right.
Okay. But effectively, I'll tell you, when you look through the documentation later on, there is a set scale actually. I imagine there's another argument that I'm missing there that tells it about how to set the scale. But yeah, the main thing is just to make sure the scale gets set to 0, 0, 0. The other way that you could do it is if this was a flat list of objects, you would get each element in that list that is a scale value. So every fourth iteration of the list, and you just set that to 1. And that would remove any of the scaling that's gone on at that point. Okay, moving on, let's put our scene back together. A lovely, exciting scene. The next one is that matrices make it really easy to mirror things across all kinds of axes. It's a way of manipulating things in other spaces. But the really nice thing about this is that it's going to deal with your transform and your rotation all in one. If anyone's tried to mirror Euler angles in the past, it is a real pain. All sorts of things can go wrong when you do that, especially if you've got things that are rotated in all the different axes. It can be very difficult to get a reliable outcome on the other hand. Matrices make that very easy. So, as always, the first thing we're going to do is get cube 1's matrix. And now the next thing we're going to do is we're going to declare a mirror matrix. And what this is an identity matrix with the aspects that we want to mirror manipulated in it. So we want to mirror this matrix about the y-axis. So what we've done is for the first row in the mirror matrix, we've set the x value to -1. And that's actually all we've done. So we've just said, flip everything over in the x-axis. So we'll declare that. And then the way to apply that mirror matrix to our cube matrix is to multiply the cube matrix by the mirror matrix. And the reason that the rest of the mirror matrix is set to identity is so that nothing will happen to your matrix when it happens. All those other values, once they're multiplied, will come out exactly the same as the way they went in. So you'll end up with this new matrix, which you'll see is the same. Oh, have I actually done that? Let's have a look at that. There you go. It's exactly the same as this first one, but you see that this x value has been flipped over. And if I go to the end where the position value lives, you'll see that 7.2 has been flipped over to -7.2. And then when you apply that matrix, it goes to the exact equal but opposite position in the scene. And you could do the same thing in the y-axis or the z-axis by just changing which row in the matrix you want to flip it over. And that's a really nice way of doing very simple mirroring in a scene. And you can keep playing with that forever, and it's lots of fun because you can do that all day. And it's going to go back to the exact same point when you mirror back. Another nice thing about the matrices is just the accuracy that you get. You'll see that there's an enormously long floating point number after each one of these things, far more than you get in a channel box. It means that the accuracy is very, very high, and you won't get many floating point errors. Okay, so that's sort of 3 very simple applications of the matrix. The other thing that I wanted to talk to you about is the idea of storing storing an object's position relative to another object. So I'm going to type this one from scratch. The very first thing we're going to do is we're going to get the matrix of the objects that we want to store the position of, and we're going to declare the position of the object that we want it to be relative to. So, I think I've already written this a couple of times up here. There we go. So cube matrix 1, we've got that up here. And let's get cube matrix 2 from somewhere else. So the way that you put an object's position into the local space of another object is to multiply the source matrix by the inverse of the target matrix. So what that looks like in these terms is that we are going to say my local matrix, which is what you're effectively getting. You're getting the local matrix of this object. You're just saying that it's local to this other thing. When you look at a controller, in a rig, everything will be a local offset, and it's always local to its parent. We'll talk a bit more about that later, but that's what's going on at this stage. So we're going to say that we want our cube matrix in the space of the second object, and the way we do that is multiplying it by cube matrix 2 dot as matrix inverse. Okay, so that gives you the inverse of the first matrix. And if you work with any libraries, particularly maths libraries, there will always be a method for returning the S matrix inverse. I'm not going to delve into all the maths behind that today because that would just be a rabbit hole. These are the things that you call. And you store this local matrix. Now we've got that, let's say that we want to apply that offset to this object. And that's going to be way off here, and it's going to be rotated a little bit. Now again, this is a situation where if you were trying to do this with just position, it would probably be fine to just do this with flat old mathematics, got asthma on the brain. But if you were then trying to work out the relative rotation of that, it would be a real pain. So what we're going to do now is we're going to put this new matrix, and we're going to put it into the space of this object. I could also put it in the space of identity by multiplying it by identity, but I'm going to put it into the space of that other object. So the first thing we want to get, we're going to establish our new matrix. This keyboard, I have to type super slow. So the way that you restore this is by getting your cubes matrix. First thing we're going to have to get is the new target matrix, which is cube 3, that green one over there. Because that's what we're going to put it into the space of. So you take your local matrix that we established earlier, and we're going to multiply that, just a straight multiplication, by cube matrix 3. Okay, and that's given us our new matrix. Now when I apply that matrix using X form, X form, we want to move cube 1, I want to move it in world space, we want to provide it with a matrix, which is our new matrix. I haven't tried this yet, so let's see if it works. There you go. So that object now has maintained the exact same offset as it had from the yellow cube, only now it's relative to the square cube. So you can see how this is very useful in something like a pose library, where you might want to paste a pose relative to an SRB, relative to another object in the scene. You might want to remove the rotation from that pose and just paste it relative to that. That's a very, very handy way of working with it. I'm also going to redeclare all of that. I've moved the green cube, and now it's going to be relative to that. I'm going to move the green cube over to here, and it's all going to happen again. Okay, so that's a really nice way of maintaining that offset between two objects. The other thing that you could do at any point here is simply do the multiplication by our identity matrix that we declared earlier. And what that's going to do is put it into the space of origin. So it's going to move that object back to the origin, but with the offset we've maintained. Now, this mathematics here is exactly how a skeleton is driven. It's how Pose Library is driven. It's how any of our pose comparison tools are driven. And it's how most animation works. Because when you have a skeleton, you don't store the world space location of everything. All you do is store the local rotation, and you do everything relevant to the parent above it. Okay, so the way that this would work in a hierarchy, and I actually think at this point it would be easier to move back to the whiteboard, because I don't want to go too much into the Python side behind this, but I want to give a very quick example of how to derive a world space matrix. Oh yeah, you can pause that. I want to derive a world space matrix from only local space transforms. The reason you might want to do this is normally because if you try and read in something like a mani file, well, if you pass a mani file and return that back to you, you will only get local space information. Now you can derive the world space, oh that's good, you can derive the world space matrix with only the local space matrices and a hierarchy, and that's the important bit. So I'm going to give you a very simple hierarchy, a bone hierarchy. And we've only got the local space of this. So the only information that we have is this object's matrix relative to this, and this object's matrix relative to this. So what we need to do is we need to pick the furthest point in the chain and say, get this local space matrix, and we're just going to call that LM. We're going to call that LM, and we're going to multiply it by the parent matrix. So we get the matrix from this object, and we multiply this by it. And that gives you this cumulative, the next stage. Let's just call that 1, and we can get 2. So now you've got the multiplication of those two, and that gives you the position of this object. And we're going to multiply that again. We're going to multiply this matrix by this object's matrix, which is your root when you come to the end. So that's going to be matrix 3. At the end of that's matrix 2, which is the accumulation of that, and then that is multiplied by M2, and that gives you, so at that point, that derives the world space matrix of the point at the end of the chain. You can do this with any other point in the chain. What you have to do is just make sure you go from child to parent. So if you were writing this in Python, I'll do this as a very simple way of doing it without using any recursive files. I'm just going to use a while loop. The way that you would do that is you would get your child with an L in, and then what you would do is whatever, and then you would just say, and then you say the parent, which normally equals like child dot get parent. There's normally some kind of, you can list ancestors, whatever you like to do. And then what you would do is you'd say, while parent, so basically while it's none, you would keep going through this list. You would get the matrix of the child, get the matrix of the parent, multiply those things together, and then set the child to be the parent, and do it all over again. And what you'd be wanting to do is what you'd be doing up there is you would have a none, something like that, or whatever, and each time you do this multiplication, you would just keep storing that. And then when it runs out of parents, so it goes, get this, multiply it like this, okay, cool, do that, now the child is the parent, get the next parent, get that, and you keep going down that list until you run out of parents. And that's the way to do it. The other way that I would write this, I would probably not use a while loop, I would write a recursive function to do that, but that's a whole other talk. The while loop's pretty good. But as a very simple aside, I'm sure you all know this, but if you ever do a while loop, make a counter called like a counter that starts at 0, and at the end of every single iteration, just add 1 to it, and then here you just say or 100 or something, and what that does is it just says while there's a parent, or if the counter hits over 100, stop the while loop, because if you've made any bugs in here that means that it can't exit the while loop, it will just do that forever until Maya dies. Helen?
I recently found out that if you do a while loop and the counter is based on the number of things in the list, and you're subtracting things from the list during the loop, it doesn't count, and it will go for infinity.
Yeah, that's why I also like to have a like an external counter that you can. So in the case that you're having, what I would probably do is I'd say every time you remove something from the list, knock a value off the counter.
Oh, but it's a recursive. Well, I've solved it with the recursive.
Oh, no, there you go, the recursive function wins. Anyway, the other thing you do is that Python does actually have a variable deep down inside that lets you set the limit of recursion. So to stop something from going forever, I wouldn't recommend doing that because you don't really want to mess with Python's internals.
I think it automatically does have a recursive.
Oh, it has one that is very, very high. You'll be going forever.
Well, for me,
it does that.
Kicked off after a few seconds. It was like, I can't keep doing this now.
It depends how much you're doing in your while loop. If you're doing a very small thing that takes, tiny little milliseconds, then that won't make a big effect.
Yeah.
A bigger function's going to do more. So that's some of the more advanced applications of matrices. So we've got mirroring and we've got multiplying matrices up a chain in order to derive world space matrix, and we've got obtaining objects relative to other objects. Transforms. Okay, so that's quite useful. So we're going to go back onto the computer and I'm going to introduce you guys. Some of you might have already used it, but we developed an F matrix library as part of our script system. I'm probably actually going to bring up PyCharm for this because it will be nicer to look at. Let's just close everything apart from this so you don't have to look at all my other stuff. Close others. So the F matrix library, there are quite a few bits in here, but there's a few that are relevant to everyone. One thing you'll notice at the top is that we've used OpenMyers vector class because it's very good. It's got some really nice methods in it. It's very, very fast. We've used the NumPy matrix class and we've used the NumPy inversion thing as well. If you need to get the inverse of a matrix, we get that as well. The matrix class of NumPy is actually deprecated and has been replaced with just straight up arrays. So what you do to declare a matrix is just make an array of arrays. We're probably not going to be changing on NumPy version anytime soon, so if you still want to use matrices, they're still going to work. They are, in essence, just, they are simply just an array of arrays anyway. So it's just a case of cleaning it up. We've got get matrices over time. Let's go to our main one. So the main things that we have is a get matrix method, and we've got a set matrix method, which actually isn't called set matrix, and it really should be, and it annoys the hell out of me. So what this does is you provide it with an object, like a cube or something. You say what you want it to be relative to. If you flag empty, then it's just going to return an identity matrix. And it actually has a flag here to remove the scale from a matrix as well. So another good reason to use this library is that it's going to do all of your scale removing. We do it in quite this is our method for removing the scale, where we get the length of each of these scale matrices, and we work it all out this way to make sure that you always end up with a sensible scale. But you don't want to be doing this every time, so just use this one. That's always set to true, because you so rarely want to involve the scale in any of this, that by default is that. And you'll see that what it actually does is it retrieves a NumPy matrix. If you've flagged it to be local to another object, so you might say cube1 local to cube2, it does that multiplication there. So it takes your first object multiplied by the inverse of the second matrix, and it returns that. If you don't set it to be local to another object, it just returns the world space matrix of that object. The other side of that, the flip side of the coin, is set transform relative. Why is it called that instead of set matrix? I will sort that out one day. And what you provide that with, oh, I know what that is. You provide it with the object, you provide it with the matrix of the object that you want to use. This could be made easier. And you provide it with the relative matrix. So that's the matrix of the object that you want it to be relative to. Now, the reason that you supply the matrices as arguments here is because otherwise you are continuously querying objects for their matrices, and you probably don't want to do that. You want to be in control In the situations that this has been used, for instance, recovering an animation and placing it on every single pose, you don't want to be always getting that stuff because you've probably already queried all of those matrices.
Is it cached?
Well, the idea with this is that you have all that data in advance and then you apply it through these. I'll probably write a convenience method just called set matrix that just does this, but all you do is provide the object and the second object, and it will get those matrices out for you. So what we've done there is the same as we went through earlier, which is just going to multiply that object by the relative matrix, and that gives you the new position. And we're going to export that. The only other thing to notice here is that the final matrix, it has this dot A1 at the end. So a NumPy matrix, as I said earlier, is an array of 4 arrays, and the way that Xform interprets a matrix is as a flat list, not as a 4x4 array. So when you call A1 on a matrix class in NumPy, it gives you the flat, just a flat method of that list. And that's the only reason that we do that. So that's the set transform matrices ones. The other really useful ones we've got in here, we've got get matrices over time and set matrices over time. So you can give it a whole list of objects and say get the matrices for all these objects on every single frame in this animation. And then on the next, on the other one, it is going to say, well, get all that data and put it back on again in the order that I got it in. It's worth saying that this library is optimized and micro-optimized. This has been through the profiling so many times that it really is, I'd say, the quickest way to do any kind of matrix maths. In this case, there's a couple of other simple functions. The chunks function takes a flat list and divides it up into chunks. That's really good if you need to take a 16 value flat list of numbers and break it up into the 4x4 matrix. That'll do that for you. It comes back as an iterator, so you just need to convert it to a list when you're done. The only other bits we've got in here are serialization methods that let you just cast all of this information in and out of JSON. Most of this is used as the backbone for our new pose library and some of the old pose library. It's why the new one's going to be significantly faster than the old one, because we've got this library to draw on. The only other bits I wanted to cover on is examples of scripts that we've already used. So as I mentioned earlier, the align over time script uses this. We've got the pose library, relies on this very heavily. When we first started making pose library, our rigs weren't very uniformly built, which meant that what we had to do is make sure that every part of the rig could have the data about it stored in a pose without actually having to think about what the transform and the translate and rotation settings were set to, because they were not always frozen, they were sometimes wrong. And also when you came to mirror an object, that became very difficult, because if one shoulder was frozen and the other one wasn't, it wouldn't be able to mirror correctly just using attributes. So what we always had to do is we would have to consider everything in terms of mirroring the actual mesh. So every aspect, you know, the bind pose, the reason we have a bind pose is that the bind pose determines what symmetry looks like for that rig. And then in the animation, it would store every single one of those controllers relative to the bind pose, mirror it, and then paste it again back relative to the bind pose. And what that meant is that you were always referring back to this example of symmetry, even if the rig got completely screwed over. That's also another reason why if you don't keep your bind poses up to date, pose library breaks horribly, because it means everything's referring back to this crooked data. Keep in place was another example of a script that we used very heavily on Planet Coaster. That was for, we had an animation of a guy walking, sitting onto a bench. That couldn't be motion extracted in the game, so what we did was we got a locator that basically did the linear movement. The whole animation was then put into the space of that locator, and it was exported on the spot. And it looks weird because the guy just kind of steps on the spot. But when he goes back into game, that's clipped onto a locator that's doing exactly the same thing, and the end result is that it looks exactly like how you authored it. There's a talk that we did about that I can give you guys access to. Also wrote a Medium article about that if you're interested about that. And the climbing script in Planet Zoo does very much exactly the same thing. And that's the end of the talk. That's everything that I wanted to sort of cover in my notes. Are there any questions? Is there anything that I covered here that didn't make any sense?
I got a little bit mentally stuck on the starting at the end of a joint chain and going back to find their world space matrices. I thought if you grabbed like the end of a joint chain and you were like X form query matrix tree,
Yeah,
it would
yeah,
give
that,
you.
that absolutely does work. So you can in my use XFOM. The reason that I wanted to mention how you derive those from that is so that it's more about how the game would interpret it and how a skeleton is interpreted. So it's more about understanding how the software actually uses that. Also, like I mentioned earlier, our animation files actually only store local transforms at all. So if you pass a mani file and you're trying to pose a skeleton based on a frame of a mani, the only information that you're going to have is local space information for each joint. And then you'll have to derive the hierarchy from the model file that determines the skeleton. And then you'll be able to use the combination of the hierarchy from the skeleton and the local space matrices that you've gotten from the mani file, start at the very end of the hierarchy and roll back up to the root. If you were writing a script, today, I would not recommend that you did that at all. That wouldn't be a practical use of time. I would just use XForm and I'd just say, give me the world space matrix of it. But when you call world space, when you're calling that is exactly what it's doing. It's going all the way up the chain, multiplying, accumulating these local things, and then the thing that you arrive at the end is the world space matrix.
So X-form matrix, just, it works internally, like if you're like, I don't know, 10 levels down, the child, it does that by looking up.
Yeah.
So would it theoretically be slower if you had something that was like the millionth child in a chain?
No, because the matrix attribute of an object is calculated when the graph is evaluated. So when you move to a frame, Maya is in the background updating that value.
Okay.
So by the time you call it through XForm, it's already been worked out. That is why, if you're ever trying to get the world space matrix over a timeline, that's why you can't just query that attribute. Because you know how you can sample, you can evaluate, say like translate X on every frame of an animation without having to move the time slider. You don't have to do that. You can just say query that. That's because all that information is already in the graph. That information for the world space matrix isn't in the graph until the graph has been evaluated. So every time you want to capture the matrices over a set amount of time, you will actually have to move the current time cursor along and force the graph to evaluate on every single one of those frames as you capture it. We've tried a million other ways around it. We can never get it to give us the right results. If I ever find one, I'd love it. But one thing I did find is that there was a bug that Autodesk acknowledged, that it wasn't returning the correct world space matrix as in the attribute at all, and that's been fixed. There's also been another thing added to Maya 2019 and Maya 2020, which is this idea of an offset value that you can have on every bone, and that's using the same sort of thing, just allowing you to have this extra offset from another joint. It just might be a very useful thing. It's something that you can use. You could eventually use it entirely instead of constraints.
All right.
Yeah, which would be an interesting use of that. Anything else? Any other questions? Have I managed to do? I've done this in it's exactly 6 o'clock.
Well done.
How about that? That's some sort of magic. I really hope I didn't bore you all to death. It's not the most exciting topic, but it's interesting nonetheless.
It's been nice and concise, and knowing what F matrix is.
Yeah. Yeah, I mean, to be honest, all of this thing can be cut down to just fucking use F matrix. Just, I mean, you don't need to worry too much about that.
I'm going to use matrices now.
Use them matrices.